Hey guys, in this particular video, what I wanted to take a look at was the general behaviors of exponential functions. So I have GeoGebra loaded up right here, and I've already set up a few interesting things that we want to take a look at. The first thing is that f of x over here is equal to 1 times 2 raised to the x power. So if we look at this red graph right here, this red graph is actually showing this particular function f over here. And I've already taken a moment to put some key points along the graph, which are a through e. And you can actually see over here on the right hand side a table that gives the x and y values of the critical points a through e. Now, what's interesting about this function is that I've set it up with two sliders. The first slider, a, will actually change the number 1 right here, which is a multiplication to the exponential function. And the reason for that is because if you actually look at how an input would look like for any exponential function, in any college textbooks they would say that the function for an exponential would always look like a times and something called a base, which I'm using the letter b to represent in this case, raised to the x power. And if you look at that, it creates this black function p, which follows this entire red function. So remember, the general form of that was a times b raised to the x power. Now, what we want to investigate in this particular video is what happens when we change the values of a and b. So as I drag a, what you're going to notice is that all of these critical values will change their positions, and over here in the table you'll be able to see what the impact is on x and y. Well, from what we've talked about in class, we already know that the x values should not change, but the y values here absolutely should change. And you can see as I start to drag the value of a, overall the values begin to stretch upwards, and this is nothing surprising given that we've already studied that the transformations that we would expect to see when you multiply something in front of a function cause a vertical stretch. Now, what I want you to pay attention to as I change the value of this base right here from 2 to a higher number is this critical value c and the critical value d. If you look right now, c is at a height of 1 and d is at a height of 2. But if I change the base and increase it instead to a value of 3, c actually stays put. I'll change it back to 2 and just watch what happens with critical value c. You can see no matter how we change its value, that c will always be at a height of 1 no matter what. But d, on the other hand, is always changing to match whatever the height of b is. So for example, when b is equal to 3, d is at a height of 3. When it's equal to 2, it's at a height of 2. And when it's equal to 4, it goes all the way up to 4. And this slider can go all the way up to 5. Now, what's happening here at x equals 2, and in the table you can look right here and see where x equals 2, what you're getting here is this idea of b being 5 and then being squared. So if I actually zoom out here, you can actually see that e has gone all the way up here to 25. If I slide the slider back down for the base all the way back down to 3, you'll notice that e actually went right up here to a height of 9. So what this is telling us is that c will always be located at a height of 1, d at a height of whatever our base is, and then e, which is always located right here at x equals 2, will just be at whatever the height of the base squared is, and that perfectly makes sense. Now, this right here is true for the general shape of any exponential that has a base greater than 1. You can see that the graph kind of looks like an airplane starting to take off, and then it climbs very, very quickly. An interesting side effect happens, though, when we let b be smaller than 1. So if we let it be 1, you'll notice that it just completely becomes a straight line, but then when we go less than 1, suddenly the shape of the graph changes. Instead of it being an airplane that's taking off, it looks more like an airplane that's landing when it comes down. And if you look at what happens here, c still is a critical value at a height of 1, but now what used to be on the left-hand side of the x-axis is now on the right-hand side. So if you don't follow that, think about this. b is a base of 1/2 right now. If I were to slide b all the way over to 2, you would see the exact same graph, only swapped around. if you're having problems seeing that, let's take a look at what this would look like compared to the original function p. What you can see with p right here, if we actually look at p from the standpoint of redefining it, so let's come here and change what it says. What we're going to do is we're going to change it to be that we want a raised to the 2 power, a times b raised to the 2 power in this case. And what we see when we do that is, a times 2 raised to the x power. What we're going to see here is this black exponential right here, which is the airplane taking off when the base was equal to 2, but here we have this red line where it's going down. And you can see that the point that was right here at x equals 2 is now over here at x equals negative 2. So when you have a base that's smaller than 1, you can always think of what would it look like if that base was the same whole number version, and then just flip it around the y-axis, and you should get this right here. And we'll talk about how that will look with some further transformations in class in a second. But what I want you to do right now is go ahead and pause this video, and I want you to think about what this graph would look like if I were to say that I wanted you to think about what the pink graph 1 times 3 to the x would look like, knowing everything that you know about this red graph. So go ahead, take a moment, pause the video, think about what 1 times 3 to the x would look like, and when you're ready, go ahead and press play and you can compare your answer to what we have here. Okay, now if you look at what happens here with your pink graph g of x, 1 times 3 raised to the x power, you'll notice that it follows the same general idea as the red graph. Turning off the red graph, which is just 1 times 2 to the x, you can see that it still follows the same general shape, but now instead of it crossing at a height of 2, it crosses at a height of 3. This shouldn't be surprising because if I change my base, you'll see that all of my points line up along that pink graph right there. But what is interesting is to compare what happens when you have two exponentials with different bases greater than 1. If you look at what happens, when the red line right here, which has a base of 2, goes past the x-axis, suddenly it starts to go underneath the pink graph right here, which has a base of 3. But over here on the left side, the exact opposite is happening. The red graph, which has a base of 2, is actually above the pink graph, which has a base of 3. One other additional thing that you also want to notice is that when you are looking at the left and right hand side, the general behavior is that if the base is smaller, on the left hand side it will be higher than other exponentials that have a larger base, but then it changes its behavior once it crosses at 0, 1. And no matter what base I change to, that particular critical value will always be 0, 1. And then the behaviors will begin to change in a way that is very predictable. Bigger bases on the left-hand side will be underneath, where on the right-hand side they will be above. So if you have any questions, just think back to the parent graph that we made, which is just any number raised to the x will look like an airplane taking off. If the base is smaller than 1, you can always rotate it around the y-axis, and then it'll look more like an airplane that's going to be landing. And from there, you can pretty much figure out graphically at least the general behaviors, which may help you to solve some of your more complex algebra problems later on.